So this new chapter is a second way to design control systems. In the previous chapter, we learned how to do it, analyze the system stability, design controller, and so on, compensator basically in S domain using Ruth Lucas. And you might wonder, why should we learn a different method now? If Ruth Lucas is working, what's the need for the frequency response? And we have to tell you that this method has its own advantages and its own applications. Well, first of all, what do we mean by saying frequency response? Let me first clarify that. Then we go back and see why this method is useful and worth looking at. So, as it says, it's the steady state response to a harmonic input. So if we here assume that we have a system with a transfer function, then the frequency response means I give it an input where the input is a harmonic function. So let's say amplitude A and frequency omega. Okay, and then if I give a linear system with transfer function G, a harmonic function like U, then you can show that the output will also be another harmonic function, while the magnitude of it, the amplitude of it is different and the phase of it is different. So the magnitude will be modified if magnitude or amplitude of input is A. For the output, it's going to be A times magnitude of G at that frequency omega. And then while frequency of the output is still omega, but it has a phase shift, where that phase shift is the angle of G at that frequency. Okay, so you see that I need two things. One is the magnitude of the transfer function at that frequency, and the other one is phase of the transfer function at that frequency. And how do I get them? Well, I get them by first we're going to replace for S equal J times omega in the formula of GS, and so it gives us G of J omega, which is a complex number, and this complex number has a magnitude, and this complex number has a phase or angle. And these two functions will change based on the frequency. So if you change omega, these two would change. And so that's the meaning of frequency response, which means output in response to an input, a harmonic input. So now let's go back and see why this method worth looking at. First of all, this method has been developed over time, mostly in 30s and 40s by Bode, Nyquist, Nichols, and others. So there is not one person. And one thing is the relation between this method and the transient response is indirect. Mostly we are looking at the steady state response of the system to a harmonic input. So we might say, what about the transient? And I'll show you that later as we go through. If the system is a second order with omega n and zeta, then you can find the relation between performance parameters in the frequency domain. We're going to see, call them phase margin, gain margin, and so on, and zeta and omega. But if it is a first order or higher order system, it's kind of implicit, not explicit. But so we mostly focus on the steady state response. But one of the biggest advantage, although this method, one of the good thing about this method is not only it can be used in classic control, it can also be used in one of the branches of control that I don't know if you heard of or not. It's called robust control. And the other one, to some nonlinear control systems, it can also be used, okay? But the biggest advantage of this method is experimental determination of the transfer function. So let me tell you what I mean. So not always this g of s is just easy to find, because in order to find g of s, you need what? You need, a differential equation between y and u, and then you apply Laplace and find y of s over u of s, which is g of s. But not always the system is easy to mathematically model, right? Some systems are very complicated and very hard to model, so we really cannot easily find a mathematical model. And then you might say, well, if I don't have the governing differential equation, how can I possibly get g of s? And the answer is this: you do it experimentally. So here you assume that this is a black box, okay? I have no idea what's going on in this system, but I can pass to the system an input with some frequency and some magnitude, omega and a. They are under my control, and then I can measure the output of that system, right? Let's call it b, so the new magnitude is b times sine of omega t plus some angle phi. And then the thing is, b is a function of omega, so if I change omega, each time I get a new b with the same a. If I keep a the constant, just change omega, each time I get a different b, and each time I get a different phase. So I can plot them, right? I can plot them versus the input frequency, and I will get some plots, and then based on those plots I can determine, based on these two guys, I can determine the frequency response of the system. Okay, so these plots, we have different names for them. The most common one is Bodyplot, which we're going to see today, start at least on it. And based on those, I can determine what type of system this system is. I can determine the order of that system and a bunch of other things about it. So I can experimentally kind of infer what's inside the system based on this magnitude and phase plot that I will get. Okay, so we'll work on that. But one of the things that we have to know, one of the terminologies probably heard, but is decade and octave. So decade is a frequency range between any omega, doesn't matter, the initial one, and 10 times that frequency. It's called a decade. And then between any omega and twice as big, we call it octave, right? So between 100 and 100 and 1,000 is called a decade, but between 100 and 200 is called an octave. Good. So let's go back and look at this idea of a frequency response that I just mentioned, that if you have a system and you pass to it a harmonic input, then the output is also harmonic with modified magnitude and modified phase, where that modified magnitude and phase, they both come from what? The complex g of j omega. So in g of s, instead of s, we plug in what? J omega. So now g of j omega will be a complex number. It has a magnitude, it has a phase. So now we want to do that for a first order system. We want to know if the transfer function is k over ts plus 1, a first order system. What is going to be m of omega? In other words, how does a first order system modify the amplitude of the inputs, right? Because m omega is what is multiplied by input amplitude to get output amplitude. So it's the multiplying factor. So let's look at that and see how a first order system changes the response of the magnitude of an input. So k over ts plus 1. So let's do that together. So if we come here and we say, well, g of s is k over ts plus 1. So the first thing we always do is we plug in for s equal j times omega. And then what would you get? You get g of j omega is equal to k over t omega j plus 1. By the way, this j is the same as I, right? That's the same thing. So now this is clearly a complex number. The numerator is a scalar or just a real number, but the denominator is a complex number. So if I ask you what is the magnitude of this, what would you say? Which, by the way, we call it m of omega. What is that? Well, we know that it's a ratio, so the magnitude of a ratio is the magnitude of numerator, k, divided by the magnitude of denominator. And magnitude of any complex number is always what? The real part squared, correct? Plus the imaginary part squared. So that is the magnitude. And clearly you see it depends on omega. Now if I want to plot this guy, where omega changes from 0 to infinity, right? How does it look like? So if I plug in omega equals 0, what would you get? Yes, k, right? Because the denominator will be 1, so you're going to get k. And what happens as I raise omega? Well, of course, the denominator gets bigger and bigger, so the whole thing will get smaller and smaller, and it kind of shows this kind. Ultimately, as omega goes to infinity, the whole ratio goes to 0, so I expect kind of behavior like this. And I can plot it with MATLAB too if you want. So I can give them a number, let's say k equals 1, and then t also equals whatever you want, doesn't really matter, let's say 2. And now we say omega is equal to 0 with some increment of, let's say, 1 to a big number. Let's say 10,000 is enough for us. We don't really need to go to infinity. And then m is equal to k divided by square root of 1 plus t squared, right? Times omega squared. Okay, yes. Don't forget the dot. And then we plot omega versus m. And yes, now since 10,000 is so big, you see this one is just going down and going to 0, but it is doing it over a short period of time. So if you can see here, I zoom into this area, see this is what's going on. So it is going way faster than I expect. And maybe I just do it over a shorter range of frequencies, maybe up to 100. And let's plot it again. So yeah, now we can see it better. And there is a little bit of curvature here, but again, it is over some short omega. So if I want to really correct that, if I go back, this thing is not exactly like that. It's kind of like it's going very fast. This is going quite fast like this. Okay, and so you might say, well, what does it mean? What's the meaning of this? Well, look at the meaning. The meaning is if the frequency is low, right? So let's say if we divide this into two ranges, low frequency and high frequency. In the low frequency range, the number, which is always less than the input, right? So let's say k was 1. So the reduction is not too much, but when you go high range of frequencies, what happens? It is gonna get bigger and bigger. So this kind of filter, or you might say, what is filter? This kind of behavior is what we call a low pass filter, which means if the frequency is low, it allows the input to not be modified significantly. So if the input magnitude was 10, maybe the output magnitude could be 5 or 6, so you still hear it, right? Let's say it's a musical device, right? It's a musical filter. So if you pass a sound wave of frequency 100 hertz with magnitude of 10, the output is also again 100 hertz, but the magnitude of output is instead of 10 is 5, so you can still hear it. But if you pass to it an input with a frequency of 10,000 hertz, then since this number is really small, right, maybe 0.001, then if the input is 10, the output will be what? 1 over 100. So you can barely hear, right? So it is filtering away, it is suppressing high frequencies and only let low frequencies pass by. So we call it a low pass filter, right? Now similarly, I can show you if the transfer function has an S in it. So still first order system, but it is something like this. So the previous one was k over ts plus 1. This one has k times s over ts plus 1. Now what kind of behavior this one shows? So again, if I plug in s equal j omega for you, you see that g of j omega will be k j omega divided by tj omega plus 1, and so the magnitude of this is going to be the magnitude of the input, which is k times omega, divided by the magnitude of the output, the denominator, I'm sorry. So it's going to have this extra omega, and the question is now, what happens to this? Well, when omega is 0, what happens? When omega is 0, well, this magnitude goes to 0. And when omega goes to infinity, what happens? It's infinity divided by infinity, so if we take the highest order terms, it's going to be a limit, right? So the limit of g of j omega as omega goes to infinity will be k omega divided by here. This t omega is much bigger than 1, so we can neglect 1 in comparison to t omega. And so if you neglect this, now you have a square root of t omega squared, so that the square root and the square would cancel each other, so you're going to get t omega. And so if you simplify it, you're going to get k over t. Okay, so at 0 it's 0, but as frequency goes bigger and bigger, then this number is also growing. So you kind of expect a reverse type of behavior. So this is what I do now. I make this frequency again a little bigger, and then I define my transfer function to be k times omega divided by that square root, and now I plot this for you, and now again you see that it is going up to 0.5, but it is doing it over a short period. So if you want again to be able to see it, you can bring the frequency range down a little bit, and if you plot it, now you can see that in low frequencies the amplitude is low. As you get higher and higher, the amplitude gets bigger and bigger, so it is doing the opposite of the previous one, right? So if I want to plot this again here, so it acts like this. So here clearly the low pass area, the low frequencies have small magnitudes, and high frequencies they have bigger magnitude. So what do we call this? We call this a high pass filter. So this one would get rid of low frequencies for you. Okay, so that was the difference between if we add S or if we do not add S. We go from a low pass filter to a high pass filter. Good. Now, let's start on this topic called Bodyplot, which is basically what I just did for you. This is the magnitude plot, and you also need to show the phase plot as well, the angle of the omega, and you show it on logarithmic. So this is called the Bodyplot, which shows how a system behaves as the frequency changes. So the Bodyplot again has two plots. One is the magnitude plot, the one that we just did for the first order system, and the other one is the angle or the phase plot. Now we plot both of them against a logarithmic scale. Okay, so we plot both of the magnitude and phase against logarithmic scale. That's one. The other is we don't really show the magnitude of G. Instead, we take logarithm of that magnitude, and then what? We multiply it by a 20. So instead of simply magnitude of Gj omega, we take log of that in base of 10 and multiply it by 20. Now this is a standard conversion that they do in acoustics and many other basically fields of study. So this conversion converted to a unit which we call decibel, and probably you heard of that, right? They say the sound intensity of 80 decibel means this, 120 means this, and so on and so forth, right? So decibel is a standard they use in acoustics, and that's what we do here. We convert the magnitude into 20 log 10 of magnitude. And now, it's not just because they do it in acoustics. You might say, why do they do it in acoustics? That's the important thing, is using a logarithm. The logarithm has a big advantage, and I guess everybody knows that when you take logarithm, then the multiplication will be converted to addition. What do I mean by that? So if I go back here, so we know, everybody knows that the log of a times b in any base, doesn't matter, let's say base of 10, this is what? This is log a in the base of 10 plus log b in the base of 10. So if two things are multiplied, when I take log, I can just add the logs of them together. And this is really important. Why? Because let's say I have now a transfer function like this. It is, let's say, 1 over s plus 1 times s plus 5. Okay? And I say now I plug in s equal j omega, so it's a second order system. And now I'm asking you, what is g of j omega? Or magnitude of g of j omega. So magnitude of g of j omega is what? We plug in j omega instead of s, and we take the magnitude. So it's the magnitude of 1 over 1 plus j omega times 5 plus j omega. And now we know from complex numbers this is 1 over what? Magnitude of 1 plus j omega times magnitude of 5 plus j omega. Right? Or I can write it as this if you want. I can put a 1 and a 1 here and clean this up. Right? So it's going to be the first one times the second one. So you see, it's the magnitude of the first order system times the other first order system. So the magnitudes are multiplied, right? Now if I say, what is log 10 of magnitude g of j omega? Well, it's log 10 of two things multiplied together. This one and this one. So you see, it's log 10 of two things multiplied together. So now I can say this is what? This is log of first one bear with me a second. So it is equal to, well, something happening here. Log 10 of the first one plus log 10 of the second one. Right? And the other thing you still can do is, what is the log of two numbers divided? Again, if we go back here, not only I have this rule, which is important, I have another rule that you know, where it says log of A divided by B in the base of 10 is what? It's log of A in the base of 10 minus log of B in the base of 10. So this one is also really important, which we can apply here. So it's going to be the log of numerator minus the log of denominator, but log of numerator is a constant number, it's 0. So it's only negative log of denominator, so it's going to be negative log 10 of denominator. Negative here also like 10 of the denominator. And what is the magnitude of 1 plus j omega? So it's the square root of 1 plus j omega squared, right? Or if you want, I can write it like this. I can write it like 1 plus omega squared, the whole thing to the 1/2, right? That's the same way as writing the square root. So, correct? And now what? I know another logarithm rule that will help me. And what is that one? I know the log of a to the power b in the base of 10 is what? B can come behind the log and be something like this, right? So this is another important one. So I can bring the power behind the log. So here I have the power 1/2 and 1/2, so I can bring them out. So it's going to be negative 1/2 if I factor both of them, of like 10 of 1 plus omega squared plus like 10 of 5 plus omega squared. Or 5 squared actually, right? It's 5 squared. Okay, and now if I multiply it by a 20, then that's 20, and this negative 1/2 will be converted to negative 10. Okay, so you see, I can always use these three important log rules that are very important, these three guys here on the top, and that makes a lot of powers and divisions and multiplications into simple products and addition and subtraction, and these are much easier to do, and I'll show you later how we add these logs together on the paper. So there is a reason that people use log to simplify arithmetics, basically. Now, now that we know about it, let's talk about the Bodyplot of basic transfer functions. And we talk about different types of system, different orders and types of systems. So the first one you might imagine is, what if the transfer function of a system is just a simple number, it's a simple gain, okay, like k? How does the magnitude look like? How does the phase look like? Well, the magnitude that we use in Bodyplot is going to be 20 log 10 of that g of j omega, which is simply a k. So it is going to be 20 log of k in the base of 10, and the phase is just the phase of a real number, and we know real numbers do not have a phase, so the phase is simply 0, right? So if I want to plot it, how does it look like? So if g of s is simply k, then 20 log 10 of magnitude of g of j omega is going to be 20 log 10 of absolute value of k, right? And the phase of g of j omega simply 0, because real numbers do not have a phase, and the magnitude of a real number is simply a real number. It doesn't matter if I plug in j omega or not j omega, because there is no s term here to be replaced with j omega. And how does it look like if I want to plot it? So if I want to plot this magnitude versus phase, okay, what happens? First of all, this does not depend on omega. It's just a constant number. It's just 20 log 10 of a constant number, and of course it's going to be a constant number. Now the question is whether that constant number is positive or negative. Well, it depends on this log of k in the base of 10. So we know if k is bigger than 1, then log is positive. We know if k is less than 1, then it is negative, right? So it is going to be like this, or it is going to be like this. This is where k is less than 1, and this is way magnitude of k is bigger than 1. So it is going to be a constant line. And what about phase? Well, it's quite clear, right? It's just 0. So no big deal here, just 0. So this is the Bodyplot for a constant gain. Now you might say, what if the system is an integrator or several integrators, right? Multiple integrators. So first, let's look at a simple integrator. What happens to a simple integrator? So if I go back again here, so the system g of s is 1 over s. And if I plug in j omega for s, I'm going to get magnitude of g of j omega. Of course, 20. Let's see if it allows me to move a little bit to this side. No, so 20 like 10 of magnitude of g of j omega. It's going to be what? So what is g of j omega first? G of j omega is 1 over j omega, right? And what is the magnitude of that? It's just 1 over magnitude of denominator, which is omega. So it is going to be 20 like 10 of 1 over omega. Correct? That's the magnitude. Magnitude of numerator divided by denominator. And 1 over omega is the same as what? You know, this means omega to the -1, right? And that -1 can come behind, so it is going to be -20 like 10 of omega. So that is the log of magnitude. And what is the phase of g of j omega? So it's the phase of numerator, which is 0, minus the phase of denominator. And what is the phase of a pure imaginary number, j omega? Well, it's arctangent of the imaginary number omega over the real number, which is 0. So it's arctangent of infinity, which is what? Pi over 2, right? So it is negative pi over 2 or negative 90 degrees. So if I want to plot it, what do I get? Yes, you get this one here on the left, these two plots on the left side. So let me show you here. So you're gonna get these two. Right, remember I said that the magnitude will be negative 20 log 10 of omega, so we are plotting this one. Of course, when omega is, first of all, we cannot really in this plots go for omega all the way to 0, okay? So when we plot this magnitude for this first order system, the integrator, we never let omega go all the way down to 0, because log of 0 to the base of 10 is negative infinity, and we don't want to show that. So we know for a log function, always the parts that we are taking log should be bigger than 0. So we never go to 0. We can go to very small numbers. Here it's just 10 to the negative 1. You can go 10 to the negative 10 or whatever you want, but typically we don't go super slow on the left side. So what happens now? As I said, the smaller you make this number, the log of that will get bigger and bigger in terms of magnitude, so it ultimately goes to negative infinity. But when you multiply that negative infinity by negative 12, you're going to get positive 20 times infinity. So this magnitude is growing and growing and growing as you go to the left, and that's what you see here, right? You see the magnitude is, as I'm going to the left, the magnitude is increasing. And what happens when you go to the right side? So when you go to the right side, log of omega times 10 is clearly getting a bigger positive number, right? So it's going to be negative, positive 2, positive 3, positive 4, 5, 6. But when you multiply it by a negative 20, it's going to be a big negative number. So that's what you see here, right? It is growing in magnitude, but in the negative side. So it is going to be clearly a line in the logarithmic space. So you might say, where does this line come from? So let me show you where does that line come from. But before that, we learned that the phase of this is going to be what? Negative 90 degrees. And that's what you have here. The phase of this simple integrator is negative 90 degrees. But where does this line come from? That comes from the fact that we said we plot it in a logarithmic scale. So we are going to say my y-axis is negative 20 log 10 of omega, right? And my x-axis, instead of being omega, it is not omega, it is actually what? It is log 10 of omega, right? I'm not gonna use x-axis to be linear. I'm gonna take log of omega. I'm drawing my plots on a logarithmic scale. And so what's the difference between these two? If you look here, clearly you see y is what? Negative 20 times x. So in that space where x is a logarithmic scale and y is the magnitude of g of j omega, I expect a line with a negative, with the slope of negative. And what is that, the slope? The slope is negative 20. Okay, so that's what you see over here, that it is a line with slope of negative 20. Now, the other thing is, it says the slope is negative 20 decibel per decade. So let me clarify that for you as well. So what is the unit for y-axis? We learned that the unit when we take 20 log of magnitude g of j omega, the unit for the y-axis is what? Decibel, so that's okay. But what about the x-axis? When is it that I move 1 unit on the x-axis? So I go from one number to the other. Let's say if this number is 1, how do I go to 2? What does it mean? So if x is 1, what does it mean for omega? Omega should be what? 10, right? If x is 2, what happens? Omega should be yes, 10 to the 2, 100. And what's the range between 10 and 100? What do we call it? From one frequency to 10 times that. We call it the decade. So when I move in a logarithmic scale from one number to the next number, I'm not moving 1 hertz or 2 hertz or so. I'm moving from one frequency to 10 times that. So what I'm moving from here to here is actually a what? A decade. So the unit of y is decibel, the unit of x is decade, so the slope is going to be decibel per decade, and that's why we needed to learn the notion of decade. So the slope here is negative 20 decibel per decade, and phase is negative 90 degrees. And clearly, we said as we make omega smaller and smaller, this guy is going more and more toward positive infinity. When we make omega bigger and bigger, this can be continued all the way and go to what? Negative infinity. But we typically do not continue this plot for super high or super low frequencies. Okay, because as I said, this can go and this can go. We typically limit it in a range of 3, 4, 5 decades, not more. And clearly when I plug in omega equal 1, it gives me what? If I plug in omega equal 1, clearly log of 1 to the 10 is 0. So at which point does this line hit 0? At omega equal 1. Okay, that's this intersection point. So this is clear. The opposite of that happens if you have a derivative transfer function, right? So if you have a derivative transfer function, if g of s is simply s, what happens? Well, if you plug in j omega for s, then 20 log 10 of magnitude g of j omega is going to be what? What is the magnitude of j omega? Simply omega. So there's going to be 20 log 10 of omega. And what is the phase of this? What is the phase of j omega? It's simply tangent inverse of omega over 0, so it's positive 90 degrees. So what's the difference between this case and the previous case? Well, a negative. That's all it is. The phase is positive 90 instead of negative, and the magnitude is positive 20 log omega 10 instead of what? Instead of negative, right? Instead of negative 20 log 10, it's positive. So what happens if we go back? Clearly, you can see that it means in the phase plot, of course, you are going to come to positive 90 now. And the magnitude plot, instead of aligned with negative 20 slope, it's aligned with positive 20 slope. Again, we don't continue this all the way to super small omegas and super large omegas. We just plot it over several decades. And again, the intersection point is 1 and 0. So this one is for g of s equal 1 over s. This right-hand side, and then the left-hand side, and then the right-hand side is for g of s equal s. Okay, so that's the plot of an integrator and a derivative. Now you might say, what if we have power in them? So instead of a single integrator, I have a multiple integrator. So 1 over s to the power 2 or 5 or 6. What happens? Well, the only thing that happens is this n, which is a power. When you take log of that n now comes what? Behind the log, right? And also it is multiplied by 90 or negative 90 in the phase. So what's the difference? Yes, it is still, if it's a multiple integrator, it is still going to be a line with negative slope, but the slope instead of negative 20 is now what? Negative 20 times n, and the angle goes to negative n times 90, and similarly for positive. So let me show you what I mean by that. So for example, if I say g of s is equal to 1 over s cubed, what does it mean? Or I can write it like this, doesn't matter. Then the phase of this, remember, if it was a single integrator, it was 90 degrees, right? But now since this number is n, now that n is multiplied by that 90 degrees. So your phase goes to a constant of negative 270, and the 20 log 10 of magnitude g of j omega, which for a simple integrator, it was simply what? Negative 20 log 10 of omega, right? It was for a simple integrator. Now this whole thing is multiplied by what? By 3. So you get what? Negative 60 log 10 of omega. So what does it mean in terms of plots? So if I plot it, the magnitude plot, again at 1 it will hit 0, but now instead of the slope of negative 20, it goes to negative 60. So in the next decade, if this is 1, right, this is omega equal 1, this is omega equal 10, instead of this number falling from, well, actually, you know what, 0 is here, so if I hit it here, and this is, let's say, omega equal 2, and this one maybe, I don't go all the way to, on the x-axis, to 0, let's say it's 0.1. So at omega of 1, magnitude is 0, but at omega of 2, instead of negative 20, it goes to negative 60. And at 0.1, it goes to positive 60. Okay, so it's going to be a line like this, where the slope is negative 60 decibel per decade. Okay, so it's a steeper line. And similarly for the phase plot, of course, if I plot the phase plot for you, then it is always at what? Negative 270 degrees. Okay, and similarly, if you change n, that n is just multiplied by the magnitude and by the phase. So make the slope higher and change the angle. So that's a multiple integrator or a multiple derivative.